Hello and welcome to another Portworx demo. Today we're going to talk about Portworx volume placement strategies. Now, while Kubernetes is really great for placement of things like pods and containers and volumes across the cluster where resources are available, sometimes we need a little bit better granularity of where things are placed. And so that's where volume placement strategies come into play with Portworx Enterprise. These allow for placement of volumes and replicas of volumes to support failure domains or performance strategies, and we use affinity and anti-affinity rules to achieve this. There's 4 basic types of rules that Portworx supports for volume placement. They're broken up into affinity and anti-affinity rules, and they can be applied to both volumes as well as replicas. So affinity rules are going to co-locate volumes or replicas of a volume on specific pools, nodes, racks, or availability zones, and that keeps them within a specific failure domain or on a certain performance tier within the Portworx infrastructure. Anti-affinity rules can basically achieve the opposite, and those ensure that your volumes or replicas are spread out across those different topologies and make sure that they're in different failure domains, and so they won't affect each other from a performance perspective, and you can achieve things like ensuring that you're not going to lose a volume or a replica, for example, in the case of a cloud region failure. So today we're going to show 3 different types of these placement strategy rules in our demo. The first one that we're going to cover is going to be an example of an anti-affinity rule targeting an availability zone. So in this demo, we're going to have a MongoDB pod that is set up with our PXDB storage class, which has 3 replicas for each volume. Now, this MongoDB configuration is going to have 2 volumes for the pod, one for the database volume and another for the journaling volume. And we'll show that by using this anti-affinity rule for the AZ topology key, that we're able to spread the replicas for each of those volumes out across different availability zones in our EKS cluster to make sure that we have resiliency in the case of a cloud region failure. Okay, so we've got a 9-node EKS cluster with 3 nodes in 3 availability zones here. Now, we're going to deploy a MongoDB pod that has 2 volumes attached to it. And we're going to be using our PXDB storage class, which, again, remember, has the replica set to 3 for each volume. So the likelihood of a volume or a replica ending up on a host that's within the same availability zone may be fairly high. So let's take a look at the actual anti-affinity rule that we're going to use within our volume claim template. So we're creating a volume placement strategy with the name avoid same zone, and we're targeting the topology key of the failure domain .beta.kubernetes.io/zone, and we're going to target replica anti-affinity for this spec to make sure that none of the replicas for each volume are within the same availability zone inside Kubernetes. So let's take a look at the Mongo deployment. So this is just a simple stateful set for Mongo with a single Mongo replica. And in our volume claim templates, you can see we've got 1 volume for our MongoDB data and 1 volume for our MongoDB journal. We're using, again, our PXDB storage class with the replica set to 3. And this is where we identify our placement strategy for each one of these volumes for the MongoDB pod, and you can see that we're referencing our avoid same zone volume placement strategy. So let's go ahead and deploy this. And we'll wait for the MongoDB to come up. Okay, so we've got our MongoDB running. Let's go ahead and take a look at our volumes in Portworx by issuing a pixie-cuddle volume list. Okay, so we can see that we've got our 2 volumes. And if we go ahead and do a volume inspect, we can see our 3 replicas for those volumes. So what we want to make sure is that each one of these nodes is in a separate availability zone for this specific volume. So let's go ahead and take a look at the underlying nodes. And we'll take a look at the zone. Okay, so we can see that 84.56 here is in US East 1C. Let's take a look at 43.50. Who is in East 1B. And finally, let's take a look at 9.103. And he's in East 1A. So, for that first volume, for the MongoDB pod, we can see that all of its replicas are spread out across different zones. Let's just take a real quick look and make sure that the second volume that's attached to that MongoDB pod has the same configuration and that all of its replicas are spread out across each zone as well. So let's take a look at 52.59 first. East 1B, now 91.6. East 1C, and 25.135, if our volume placement strategy is being enforced, should end up in East 1A. So this is a good example of how you can ensure that the replicas for your volumes are spread out across a availability zone or a rack or even on a different underlying storage pool within Portworx Enterprise. Let's take a look at our next example. The next thing we're going to look at is an enhancement that we've made to VPS in Portworx Enterprise 2.10. And that's the introduction of the Stateful Set Label. So this allows us to piggyback off of an existing VPS rule, and it essentially enables us to ensure that volume placement for a pod that's within a stateful set, we can control where those volumes or replicas are placed for that pod inside the stateful set. So a good example of this is, again, our MongoDB stateful set, which has 2 volumes. And let's say we want to make sure that the journal and the database volume always reside on the same node for data locality. So as we scale out this stateful set to 3 pods, or 3 replicas within the stateful set, we're going to see that both the database volume as well as the journaling volume end up on the same node. Okay, here we are back at our EKS cluster. Let's go ahead and take a look at the affinity rule that we're going to create. Again, this is a volume placement strategy. We're going to name it Mongo STS Volume Affinity. Now, we can see here we are using volume affinity. We used replica anti-affinity in the last demo. And we're going to actually target our stateful set, and we're going to use a key value pair to match app equal to Mongo STS to enable this for any PVCs that we're using. So let's take a look at our MongoDB deployment. So this time we're going to have 3 replicas of MongoDB in our stateful set. And within our volume claim templates, we're going to use a replica 1 on the underlying storage class for Portworx this time. So 1 replica for each volume for each pod in the stateful set. And we're going to tell it that we want to use our Mongo STS volume affinity placement strategy. And you'll notice that we have the key value pair for app set to Mongo STS, which is what's going to match the stateful set modifier within that volume placement strategy that we created. So let's go ahead and deploy Mongo. And again, we'll wait for all of these to come up. Okay, now that our replica set is deployed, let's take a look at our volumes. And we can see our 6 volumes that have been created here. And what we're going to do is we're going to match these up to their pods by inspecting them. And looking at the host that volume is on. So this is for our Mongo 1 pod in our replica set. And he's on 43.50, that volume. So let's take a look at this guy since he's attached on the same host as him. And this should be Mongo 1's other volume. And again, we're looking for 43.50. So great, there's Mongo 1 and there's 43.50. Let's take a look at these other volumes real quick for our Mongo 2 and Mongo 0 pods, just to make sure that the volume placement strategy is working as advertised. Okay, so this is one of Mongo 0's volumes, and that's running on 82.24. And let's see, 135. So this is probably its other associated volume for Mongo 1. And again, for Mongo 0, sorry, we're looking for 82.24. Yep, so volumes are co-located for that pod as well. And let's just verify for Mongo 2 pod that its pods are co-located as well. So Mongo 2 on 52.59. and 52.59. So we can see that our volume placement strategy worked, and it's keeping those volumes that are associated to each pod within the stateful set on the same host to ensure that we have data locality. Let's look at our final scenario. The last thing we're going to talk about today is an enhancement in 2.10 called the Namespace Label for VPS. This allows placement rules where you may have two different teams deploying the same application or the same PVC spec to different namespaces to avoid interference with those deployments since VPS is label-based. An example here would be a dev team deploying an application that labels each node, and a QA team later comes in and tries to deploy the same application within their own namespace. Now, without this namespace awareness, VPS would not be able to deploy those PVCs for the QA team. So let's take a quick look at a demo that shows how this works. Okay, for our final demo today, what I'm going to do is I'm going to show you the difference between a namespace aware and not having namespace awareness for our VPS rules. So if we take a look at a standard anti-affinity VPS rule to avoid the same node, for example, what we're going to do here is we're going to use the key value pair of app equals Mongo, and we're going to make sure that our volumes are not placed on the same host. So let's take a look at the Mongo deployment. Now, this is a stateful set with 5 replicas, and we're going to deploy into 2 different namespaces, so a total of 10 pods, but we only have 9 nodes. And so, as I was explaining earlier, since VPS is label-based, what we should see is we should see all of the dev deployments succeed, and then 4 of the QA deployments succeed, with that 5th one stuck in a pending state. So you can see we're using the avoid same node volume placement strategy, and we're using the app Mongo key value pair. So let's go ahead and deploy our Mongo into dev. And we'll watch those pods, make sure everything comes up. Okay, so we've got all 5 of our Mongo pods in dev up and running. Should see all of our PVCs in dev bound. Now let's try and do the same deployment in QA. And we'll go ahead and watch those pods. Now what we should see here is, since we've got a 9-node cluster and we're trying to deploy 10 pods and keep all of their volumes on separate nodes, we should see 4 of our QA pods come up successfully, but that 5th one should be stuck in a pending state. So let's see if that happens. Okay, so VPS is doing what it's been told to do without being namespace aware. Let's take a look at those PVCs in QA. And again, we have 4 bound and 1 stuck pending. So let's clean this up real quick. And let's look at a volume placement strategy with namespace awareness. So this looks very similar. This is our original volume placement strategy, but you can see now that we have a modifier here called namespace. And so what this is going to do is it's going to provide that namespace awareness to where we can deploy all 10 pods even though we only have 9 hosts in the cluster. So let's modify our Mongo deployment. Give it our updated placement strategy that has the namespace awareness. And let's go ahead and deploy into dev. watch all those pods, make sure everything comes up. Okay, our dev Mongo deployment is good. Now let's go ahead and try and deploy into QA again. And this time, we should see all 5 pods come up and running because we're using that VPS rule with namespace awareness. And there we go. We have 10 volumes using VPS on a 9-node cluster. So you can see how useful that can be in a shared environment where you've got teams deploying the same applications and specs into different namespaces. That's it for today. I hope you enjoyed the demo, and we'll talk to you next time.